to start to answer any questions you might have as you are going through the material, because it's not, well, it's different from what we have been doing before, as you know. And even though most recently, last time we did the case with the, I think the Dirichlet multinomial, but that was a conjugate case, right? And overall, well, it's almost like you don't need to use any kind of, well, you can, you should still use, I guess, Monte Carlo approximation to do it, but nothing like MCMC is really needed if you're doing any conjugacy. But this time, things are quite different. Okay, Elliot is here. So, hi, Elliot. Can you hear us? Right, hi. All right, sounds good. Yeah, we can see you. That's good. Okay. So yeah, I was just saying this time, this one is slightly quite different actually from what we have been doing so far. Especially I added a couple of more material about multivariate normal, because in this case, when they are doing their model, they're using multivariate normal, not on the model itself, not the sampling model, but more about like specifying priors and stuff. So there are certain things involved about that. So I guess we can either answer any questions you have before we look at maybe one of your results, or we can just start with that, and then we all just gonna jump in when you have questions and make comments, right? Anyone has questions to ask or clarification questions, or if you feel comfortable, feel free to start sharing what you have done. And I mean, again, I hope we all feel like this environment is friendly enough that making a mistake is totally fine, like what we've been doing before the break, right? So anyone wants to give it a try?
I couldn't get mine to run at all, so I don't think mine would be that great to show.
Okay, but can you so once one of us is going to share, can you make sure that you ask questions?
Okay.
Okay, all right. Anybody got it running? It's a self-coded MCMC, and I think it's still a Gibbs sampler, so that part probably isn't that different. Okay, Isaac, do you want to do it?
So I got mine, it would sample for a while, but then like it breaks to the point that like the like truncated normal draw, or the like way he creates truncated normal draw, like, so it runs for a while and then it crashes is the,
oh, I see.
so I can, like, it looks like it's, if you sort of plot, it's, the issue appears to be with the draw of G, the full conditional draw of G, which like it looks like it's just diverging, like it keeps steadily climbing upwards until it breaks.
I see.
So I can run an example. I don't know how helpful that is. If you guys want to watch it break,
does it break?
Pull it up.
Or we have to wait for like a few minutes to break?
No, it breaks pretty quickly.
Okay, I mean, if you don't mind, we can take a look, and especially you can walk us through the steps, and then for all of us, whoever find out anything that might be helpful, just shout out, because I think once we're gonna share a screen, I mean, once Isaac shares the screen, you will have to speak up, because otherwise we won't see you. Like, I mean, I don't know. I usually just close it. So just speak up. Feel free. Okay. All right. So Isaac, can you share your screen? I might have to make you.
Can I find it real quick?
Yeah.
Where did I? Oh yeah, here we go. Okay. So I'll walk you guys through it, and there could easily be some fatal error that it was obvious I missed. I've got to go back to share my screen. Sorry.
Yeah. No, it's fine.
All right. Is that sharing?
Yeah.
Okay. So like here's, I mean, I kind of just took the rules given. You'll see I experimented with using SciPy's trunk norm, and it got me to the same place. So to see what's happening to G, I'm gonna have it print G. Each run. Maybe it has to do with my initial values. Like I messaged you. It seems like mu k is like a prefixed parameter, but maybe I'm choosing unreasonable initials. So like for Z, I just go with like a normal on 0 to 5 for each entry, and then I did G. I split it up as like obviously the ends are infinite, but 1.5 and 2.5 make sense because they're right between the ordinal variables.
I see.
Like, and then yeah, random betas, and I did mu also at the intervals. So when I run it, I got a domain error right off the bat this time. So in the past, it's it would go from like G, and it would go about like it would go from like 2.5 to 3.5, and each would increase like the bin width, or kind of the space between them would stay the same until it hit like 30, and then it would crash. If I have a second, can I try to replicate with the trunk norm error?
Sure.
Draw and see if that's the one that breaks it. I'll unshare my screen here real quick so I don't derail.
So I guess, okay, so maybe, yeah, while we're waiting, I guess the first thing we can discuss is the choice of the mu. Okay, so so anybody can tell us a little bit more about the data and the variable itself, and then say like, how did you choose your mu? I mean, we saw Isaac's 1.5 and 2.5 because they are, I guess, right in the middle of the, so how many levels are in this variable? 3, right? Right? Yeah, so I guess naturally the mu you wanted to, yeah, you can break them, like break it between 1 and 2, so that will be 1.5 and 2, and 3 will be 2.5, and then you have the negative infinity and positive infinity as the way that you're doing it. So did everybody do that, or did you try something else that might change how things go? Anyone? Nina, did you choose the same values?
I was like very lost in the coding, so I didn't get that far, but like those values definitely make sense to me, considering like that's where the values were, like from 1 to 3 and stuff like that. I mean, to any extent, as long as you're not choosing some like wildly crazy value. I remember that was something that got me into trouble once last semester, which was like a really bad mu value that made no sense, and that like kind of messed up the whole sampling process. But as long as it's like a feasible value, it shouldn't matter too much.
I've successfully broken mine.
Oh, okay. Take a look now. Yeah.
So I share screen again. Sorry.
No, it's fine. Don't worry.
Okay. So using the trunk norm one, using the uniform distribution, like it goes to invalid parameters immediately. But doing the SciPy trunk norm, like you start out, it's pretty reasonable, and then it just kind of explodes to the point that like I think this part here goes to infinity, and then one of your like upper bounds is infinity, and that's still supposed to be lower than like the next G up. So yeah, this is where it broke for me. I don't know.
I see. Okay. So can we, anybody else have any comments before we look into the code, I guess, more in depth, like Henrik, Elliot, and Ted?
Nothing on my end, but yeah, I think I just need to go over Isaac's code a little bit more. I think so far it makes sense, but I'm just trying to decipher each line.
Sure. Yeah, Elliot?
Yeah, at the moment, I'm just looking over the code on the GitHub. I'm trying to see if I can spot anything obvious. Otherwise, I have a slight idea about how I might be able to fix it based on based on another project I was working on about a week ago, but I'll probably try that later today and get back to you guys. after I've spent a little bit more time with this.
Yeah, so I think, so it looks like Isaac's code at least has the skeleton. So maybe we can go into, do you mind sharing it again? So we walk.
Yeah, and can I push the version? I just uncommented some stuff that has the
Sure.
trunk one, because there we at least get the like.
Yeah, you can push it, and then, yeah, once you push
Yeah.
it, so we can access it. But then today we can still just go through yours. I mean, because looks like Isaac's code has written like different functions, right? Like different sampling functions for each parameters. And then each of the parameter, the full conditional posterior distribution, I mean, the chapter notes, I should open that in my material here. Yeah, the chapter notes actually wrote it out for you, although it's in R, but the general idea is there. So I guess part of the tricky thing is making sure that like all of the relevant material is in and we don't miss anything, because sometimes the textbook will accidentally leave certain lines of code. Sometimes, I'm not saying that for this chapter in particular, but in the other chapters that I spent time reading a lot before, so it's possible. But I think we could spend the rest of today's time going through the few functions that Isaac wrote and to make sure that we understand what it's doing. And I mean, because it involves like the Wisher distribution, right? And then certain, I shouldn't say Wisher, I should just say multivariate normal when they're doing that kind of sampling. So we can make sure that we understand it to some degree, and then we all can break to go back to check what we can do to fix the code. And then next time when we come back, we'll have hopefully a better, I mean, this is a challenging problem, so don't feel frustrated, and it's just part of the learning. So Isaac, do you want to share? It probably will still just be your Jupyter notebook, so we can.
Yeah.
Yeah. Mm-hmm.
So it's on, if you want to pull it up like on your own computer, if that's easier to see, it's the one called Hoff. It's on my folder on the GitHub. It's called Hoff Probit Sampler Trunk Norm, as opposed to Hoff Probit Sampler. So like, okay, set up. So then real quick, I'm going to pull up the Hoff text just so I can, am I still sharing screen?
Anything. Yeah, we don't see anything yet.
Yeah,
But,
okay.
Yeah. If you want to do multiple things, you can share your desktop and only just put the browser of your Jupyter notebook and then the PDF if you want on that.
Gotcha.
Yeah, and then we can see both. But otherwise, yeah, whichever you feel more comfortable, that might be the easiest.
All right. Is that any better? No?
You got it? Mm-hmm.
Okay. So the first one,
Data, right? Mm-hmm.
Yep. So it takes in X and Z because Hoff like notes that those are kind of the two elements of the full conditional. So, or the two relevant elements. So then I just transpose Z so I can get ready for matrix multiplication. I call the constant n divided by n plus 1 C, and then matrix multiplication to get the mean of the multivariate normal draw. Again, straight out of Hoff. And then the variance covariance matrix for the multivariate normal draw.
Yeah.
And then I draw one of them.
So yeah, on that, can you tell us? So we know on the text they show you two chunks of code, right? Part of it is about, I thought is about the Z, which I guess you're gonna go to next in a second. So for the beta part, can you point it out to? Okay, it's this one, right?
Right there, yeah.
So essentially, you get the X transpose and all of that with the Z, and then you calculate the expectation for that mean, and then the, I guess, the variance of that mean, and then you are doing the random draw from there.
Yeah.
Okay. All right. Makes sense. Can we go back to your code really quick again?
Yep. So, like that's kind of the that's like the most straightforward sample in the Gibbs sampler. So then here.
Yeah. Any questions from others here? All good? Okay, sounds good. And next one.
And I have a feeling at some point midway through this, someone's going to point out something really stupid why it's not running.
Don't
So
do that.
I'm bracing for it.
All right.
So for this one, I get the like all of the dot products beta times x for each entry, and then it like goes to a matrix when you do the matrix multiplication. So it's kind of clunky, but I just like flatten that into a normal array again. So then notably, so SciPy stats trunk norm, it isn't like R where you give just like mean, like you have to scale it. So we know that standard deviation is 1.
Yeah.
So like the lower bound is the z-score
Yeah.
of what would be truncated. So that's what's going on here. So for each element, like taking the z-score and then imagine this is all divided by a standard deviation of 1. So you do that for I minus 1 for the lower bound, and that's we get that from Hoff right there, and then just regular I for the upper bound, and again z-scored. So that gives you A and B, and then here's your mean.
I see.
Scale is 1.
Yeah.
Take the trunk norm draw.
Yeah.
Those, when I was going through them, like looked pretty reasonable.
Yeah. So can I ask a question there? So your A and B, are they exactly the same as what Hoff is saying, or you actually subtract your BX from it?
So it's I subtract the BX. That's the scaling step required for SciPy. So
I see.
Like to take the trunk norm, like to make A the lower bound, you have to scale it by, or you have to z-score it by BX and 1.
I see.
So I just did that inside of there, save myself a step.
Right. So if we don't do the truncate norm, which I guess is what you commented out right below this, and that looks, I mean, more resembling what the R code is written, right? For
yeah.
So that didn't work, or like what was the main reason why you moved it to the truncate norm?
Oh, I knew the truncated norm gave me the error we were getting where it diverges.
I see.
But I mean, I guess we could run it again. I think the issue is again with the G's here.
Yeah. Okay. But if you don't mind, can we go back to the AB and all the way that it's being done in Puff, like the ones that you commented out? I just want to sort of like maybe get the problem one by one. All right. So in this case, we have the A and B. The max. I mean, A is the max between the two. Mean is the minimum between the B is the minimum, and then we take a uniform random draw right from that, and then you get your Z from the okay, that makes sense. Okay, sounds good. So let's just keep it there. Maybe we're gonna like go back. To the truncate norm that you did, but I want to sort of mimic what they do, and then that might be easier for us to debug later. All right, let's.
Sounds good. And in reading too, it looked like that was a pretty standard way of drawing, like of creating a truncated normal distribution. So even when we call trunk norm, like this sort of thing could also just be happening behind the scenes too.
I agree. That would be my guess, and I just want to make sure. So one quick question. So in the instruction, in the Hoff book, they're like, so you have, let's see, you have labeled, I guess, all of the, so here, like for example, there are easy, so there easy is also a matrix, right? Sorry,
so they've done, I think, for ZI for each.
Oh, I see. So for all of them.
Yeah.
Okay.
And I guess like that's kind of similar to what's going on here because we're taking it like row wise
Yeah. Oh, I see. Right.
in the
Right. Yeah.
list comprehension chunk.
Yeah, makes sense. Okay, sounds good. All right, let's look at G. And G, I guess, in the Peter Hoff book, it's the last part, right? We set A to be the max, B to be the min, and then do this uniform draw and then get the G. So let's see what we're doing here. Yeah.
Yeah, and I'll convert it to the Hoff format.
Yeah, if you don't mind. Yeah. Mm-hmm.
Here. So the first thing, so my G was structured as like, I'll just write out an example.
Mm-hmm.
So it was like,
Right, and then
so
positive.
that way,
Mm-hmm.
when you took G of 0 or the 0th index,
Mm-hmm.
it was just returned you
Mm-hmm.
infinity.
Mm-hmm.
So like really we're interested in updating the 2 in here. Or like there's k equals 3, so k minus 1.
Yeah.
G of interest.
Mm-hmm.
So the nice thing is, so we know that k is going to be like 4 minus 2 here, minus the outer edges. So then.
So one thing I noticed, I don't know if it's that the AB, when you set the AB here, I think B should be the minimum.
Oh, yep. This is the one I was waiting for, where it was.
Everybody else, like, watch out. I mean, we should all be focused and trying to find, but who knows? Okay, so that might be one thing. Okay, so like maybe keep walking us through.
Yeah. Okay. So that makes sense. So then I do that. I just left it as A for now, and then I do a step where I scale it and then take the CDF. So I guess that's the this part of it, like a half step.
Right. So I was wondering.
Sorry.
No, Nina, go ahead.
I was a little confused, like earlier, like when I was reading through the textbook and was hoping maybe what's going on with these like sig functions or whatever it is in the textbook.
It's the sig and the mu, right? Is that what you're? So
I think I was also confused because I don't really see like an analogous version of that here, and that was definitely something that's done.
Yeah. So.
The sig vector.
Yeah.
So that's for I let sigma just be 1 for all of those. So that's like one of the parameters.
I see.
Yeah. So this is.
And so just to save myself from putting things in parentheses and dividing, not because it was a good parameter choice. So it's just like it's a 1 implied here.
Yeah, but let's stay here because Nina's question, I think, is on to the point here of about mu and sig, what they are. So in the book, I said, can you scroll up? I think it's probably on page. Yeah, it's. Maybe,
I was unable to find the definition.
Yeah, it's down. Okay, it's right below. Let's see, right below. Further a little bit more. Yeah, it's probably down here. Let's see. So it's here on the top.
I think the first time it popped, at least that I caught it, was.
No, it's on the top. So can you go up again? So I think it's on the top of 212. Yeah, so it's right above. Yeah, it's right. Yeah, just stay here. Okay, perfect. So we see that equation 12.3. That is how we are. Remember, like say G. The Z is the underlying data, right? The underlying continuous. And then we have this G function to transfer it into the different levels, right? So if we look at the first line of the next page here, the values G1 to GK minus 1 can be thought of thresholds, which we understood. So you can pass Z into Y, okay? So we're talking about here, the unknown parameters in the model include the coefficients, which we know, and all of the thresholds. And if we use normal priors for those quantities, it's not here. Where did I find it? Give me a second. I thought there was something about mu and sig that is predefined. I thought it was here. Give me a second. Anybody else found it? Like how we can define mu and sig?
So I also tried it just doing like the last G2, and that also broke.
Mm-hmm.
Like I didn't know if it was like even updating on top of itself to make sure the ranges were reasonable.
Yeah.
That's why I shot you the message. Like, do we?
Right. I understand. Yeah. So let's see. So in my understanding, the mu and mu and sig, they are really just in the particular threshold, like the range that we're working with, because mu is the mean, sigma is the standard deviation, and that's where we get. Oh, it is there. Sorry, can you go back to the top of 12, 212? So it's that sentence. Yeah, that sentence. Yeah. So here, if we use normal prior distributions for this quantities, so it is the normal prior that we give for the G. That's how I understood it. So the mu is the mean, say mu k is the mean that we give for GK. Well, there's no GK, but GK minus 1, for example. And then, so mu1 will be the mean that we give for G1. And then sig1 will be the standard deviation that we get for G1. So I think that's what, say, Isaac's point is chose mu. So there are only two mu's that we're working with, right? Like mu1 and mu2. And one of them is 1.5, the other one is 2.5. And Isaac set the sig to be 1 in both cases.
Yeah, and sigma's just 1 to make it easy.
Yeah, but in short, the mu, so going back to Nina's question, the sig and the mu, they are the they're the parameters for the priors that we use for G. Okay, and they represent the mean and the variance, the mean and standard deviation of the normal. So we can do what we're looking at right now. Yeah. So in fact, can we go back just up a little bit more where you show your JIT simulation? The step here about, okay. So now we converted everything back into G, right? And then also not using the truncated norm, but using the hot version. Okay. So can you run this part and then I guess the other one.
So with that, and then I do it like half step to scale.
Mm-hmm.
And then the uniform in SciPy is not like A to B. It's the lower bound and then the bin width of the, bin width is the right term, but the width. So that's where this comes from.
Mm-hmm. I see. Do you do that for, you did that for the other one as well, for the other view.
Yeah.
Mm-hmm. Makes sense. All right. And okay, and then we get the G from mu k plus sig, but your sig is 1.
And then like same thing.
Okay.
All
right. Let's do this to see like by correcting that max to min whether things will change.
Yeah, give it. Watch it run perfectly this time. This is. I'm hoping it. I'm hopeful here.
Are we printing? We are printing G, right? Okay.
Yeah. So it's the same, and it's again. It looks like with.
It's about the truncate form, right? Okay.
With G.
Mm-hmm. Yeah. All right. I don't. Yeah. I think I don't really sort of like understand the issue now, and I think everybody else on the call probably get a better understanding of how the code is working. So I think and also we're right on time, just to make sure that nobody's late for anything else. But I think, so all of the comments, so Isaac, can you push this again, this later to your folder? So, the added things that we did.
Yes.
So, yeah, later, it's fine, no rush. But then we can all learn from this to see if anything can be found. If there's any additional mistakes. But I guess what Isaac is suspecting is mostly about the truncated norm, whether doing it following the Hoff book is the right thing to do, because we do get error messages here, right? But one thing I would say is if you want to also give values for sig, You can easily do that by adding it to the model itself. That might be a better way to do it overall. I mean, you can always set them to be 1 later if you want, but you can get the flexibility into the model in case you want to play with it. But my understanding of the model is I will probably also give the same value for all of the sig. Because I mean, maybe 1, maybe some other values, but then I would choose the mu in a way that we were discussing earlier. That is sort of like between the cutoff points that it will make more sense for us to do it. Make sense? Make sense?
So I just pushed it. It's the one that's trunk norm,
Yeah.
but now in class at the end too.
Makes sense. And before we break, just one more comment. I was just looking at this result, I guess here. I mean, not the result, just looking at this. Because, well, we know that g is the function that would transfer the z to y, right? So I was just thinking out loud here, like for the mu, say mu1, for example, like mu, say for example, like the mu for this thing. If I look at this, should it be 1 instead of 1.5? Or I'm missing it here. You know what I'm talking about? For all of you?
For mine, I just made it 1.5 because it was right in the middle of 1, 2, 3. It's not like meant to be. The idea was it would sample away from that.
Mm-hmm.
That was just my initial value given.
I see. Oh, I see. So you do make, okay. So you do you sample mu at all? I thought mu is fixed.
Okay, sorry, it broke up. Can you say that one more time?
Yeah, so I was wondering, we probably have to look at the code more carefully, but when I was looking at the code, for example, like the code as well as the equation 12.3 here, I thought the mean and the variance or the sig, they are predetermined that we don't have to model them. And my understanding of what you did, maybe I missed it, but I don't think you ever sampled mu, right? It's not really the starting value. They are just the fixed values of the mu that you used in the first place.
Yeah. Oh, wait, but because don't we still have to initialize g because we're sampling g?
We do, but the mu's, we never change them, right? I thought
Yeah,
so.
no, those stayed fixed. I set mu equal to g just because like that made sense
Oh,
at the
I
start.
see. Yeah, yeah. So then if I'm looking at equation 12.3, I would think, well, if I'm looking at this part, well, the mu for that, I mean, I want y, which is the, well, g is the function, right? G is the function that we apply to z. So why would I use mu1 if it's labeled as 1? Why would I use mu1 as 1 instead of 1.5? Why would I want the mu values to be between 2 categories? Does that make sense? Or am I making everybody more confused?
Oh, would that like give it the g's more room to cross over? Or like, not, well, you don't want them to cross over, but like.
Yeah, we probably want, yeah, we definitely want them to be, I mean, disjoint in some sense. Anyway, so that, I mean, that is like my question to you all. And as you go through the sample code that Isaac has, maybe keep those in mind as well. And then we can, yeah, next week when we come back, we can see how everybody's doing, and hopefully there will be some progress. So I did put something together for next week, but let's just push that for the week after. So let's focus on solving this one. And again, I mean, with the online and everything, it's probably more challenging, and then you have other things to balance. So if it's a slower pace, it's fine. I mean, it's an independent study after all. So don't be too stressed out about this, but try to learn something along the ways, and hopefully you will find it useful in the long term. Okay. All right. Okay. So yeah, so next week, we're going to meet again at this point and using this link. If you have any progress, just push it to the GitHub. And next time, I probably won't ask Isaac, maybe one of the other ones who hadn't talked too much yet today, but once we get the chance to build up what Isaac has already done to see if any debugging can help, that will be really helpful. Okay. All right. Okay, sounds good. And like I said,